Okay, brilliant. We have used z-test and we have done the statistical significance test for the respective data, and we have concluded that years of experience feature. So we have concluded that as p value is greater than significance level, that's 0.05, the null hypothesis, we failed to reject null hypothesis, indicating that years experience feature is not statistically significant. So we say that we should not take it as a feature for that. Of course, you have to do further exploration and further analysis to find out to whether to decide to go and take it as a feature or not. That's keep it aside for now. But at this moment, the conclusion of the previous example that we have done is years experience cannot be used as a feature for calculating the salary based on the amount of data set we have given. There are a lot of factors which affect it, but however, I'm just talking about the data set we have given, which consists of only 30, and the final conclusion that we got here is we failed to reject null hypothesis. Hence years experience is not statistically, it doesn't have a statistical significant relation with the salary. Okay, fantastic. But the question is, do data scientists really use the significance test as what we did before? Indeed, data scientists often perform significance tests, including z-test, as a part of their data analysis process. Significance test helps determine whether there is a statistically significant relationships or difference between variables in a data set. In the context of regression analysis, data scientists may use the z-test or the statistical tests to assess the significance of individual features, nothing but independent variables, in relation to the target variable, that's dependent variable. So the purpose of z-test is to identify which features have a significant impact on the target variable and should be included in the regression model. So that's the main purpose of doing a significance test. It is to identify which features have a significant impact on the target variable and should be included in the regression model. So that means understanding significance test or z test is very important for a data scientist. It's $1 million learning for you, because based on this you can actually identify a feature which has a significant impact on the target variable, and you can include that in the regression model. So that's the reason I beg you to focus on this. I beg you to learn this. There is, don't think, see, as our courses teach us, say statistics is different and then machine learning is different. No, machine learning is heavily dependent on statistics. In other way, you can say machine learning is a masked statistics. That's it. That's how I see. So that's the reason for you learning statistical significance test is damn important. So this leads to another question. So with this, you got to know that it's prior important. It's damn important for you to understand what exactly is statistical significance test. So this leads to another question. So that is, if you observe the process, the standard deviation we have calculated for the target variable, and then we used a coefficient of the feature. Using these, we have then calculated the z-score, correct? So now the question is, how This can tell statistical significance between two variables. What is the connection between them? How it is possible? How it is possible? You know that if you know the mean of the sample or mean of the data, then you can calculate the statistical significance. But how can you have two variables, out of that one variable standard deviation you are calculating and one coefficient you are taking from somebody else, and then you are calculating the z-score and you are saying there is a statistical significance relation or not? How it is possible? Can you tell me? Put it in comments. So then this leads to another question, that is, in the context of using the coefficient of a feature to calculate the z-score for determining statistical significance in relation to the standard deviation of the target variable, does statistical significance primarily indicate the causality or spuriousness? That's the primary question. When you got certain amount of statistical significance, does the statistical significance primarily indicate causality or spuriousness? What does it indicate? 2. What does statistical significance actually mean? Not just, okay, you got the probability value directly from the algorithm and you know 0.05, and when you see if it is lesser than 0.05, it's statistically significant. If not, it's not statistically significant. I'm not talking in that way, in that perspective. When you say statistically significant, what does it mean? How does it connected with your data where you have two variables? How does a statistical significance can tell the relation is significant? The relation is significant enough. How can some numbers p-value can tell the relationship between two variables is significant or not? That's what my question. Do you know that? If you know, put it in the comment section or else wait for my answer. So does statistical significance primarily indicate causality or spuriousness? That is another question you have to answer. So now this leads to another question, which is, when you describe something as statistical significant, what does that imply in terms of the relationship between variables? When you describe something as a statistically significant or statistically not significant, what does that imply in terms of the relationship between variables? Furthermore, when you state that there is no relationship between two variables, how did you reach this conclusion from a statistical perspective? How can you tell? How can your p-value, just getting a p-value, how can your p-value can tell there is no relationship between two variables? How does it make sense? How it is possible? How can a p-value from standard distribution can tell the relationship between two variables? Yes, it's a serious question. It's a question to ponder about. If you know the answer, put it in the comments, or else just brace yourself for the action. Then, next question. When we state that we do not have sufficient evidence to conclude a statistically significant relationship, what does that statement specifically imply in the context of statistical analysis? And the last question that I just want to give it to you, I just want to ask you as a food for thought, which is, how does the p-value, which measures the probability of obtaining a coefficient as extreme as the observed one or even more under the assumption of the null hypothesis, help determine whether there is a relationship between the feature and the target variable in the context of regression analysis? That's the another question you have to ponder about. So now let's take one example. The same regression analysis, the regression analysis that we have done. We got the coefficient of 9,449, intercept of 25,792, and a standard deviation of 27,414, and we got a z-score of 1.8 and probability of 0.05. Let's take it as 0.05. Okay, so with these values, how can you tell there is a relation or there is no relation, whether the relation is statistically significant or not statistically significant using this? And sometimes they say there is not enough evidence. That's what, there is not enough evidence to say this is statistically significant. Sometimes they say there is enough evidence to say this is statistically significant. So what does that mean? What does that evidence mean? Yeah, what does that evidence mean? Why are you saying there is enough evidence? There is no enough evidence. What does that evidence mean? Do you know that? Do you really know that? If so, put it in the comments. Or else just brace yourself for the brilliant and fantastic action. I'm going to bring up a brilliant knowledge and information and put it in one place just for your sake. Now I think you're just waiting for me to answer. So I don't just answer your question, I would explain and expound in such a way that you will experience the statistical significance test and specifically Z test. So that's the reason you just brace yourself and buckle your belts for the brilliant journey. So let's begin. Let's together demystify statistical significance and reverse engineer the z-test. So as usual, the first step is to import necessary libraries: numpy, pandas, matplotlib.pyplot, and linear regression module from sklearn.linear model. So that's what I have just copied here. You can see that. Step 1 is done. Now it's time to move on to the step 2. Let's import the dataset using a pandas with read underscore CSV function and store it in a data variable name, and that's what we did it here. So data is equals to pandas dot read CSV, and this is our dataset. Okay, next step 3 is set up the input features capital X and target variable small y by extracting the years and experience columns from the data frame respectively. So that's what, these are the 3 major important steps. That's also we have done it. Let me show you. Okay, so this is what to perform in this. This is our target variable salary, and this is our feature, which is years experience. Now the most important part, which is step 5 or step 4, it's a bootstrap sample. So what is bootstrap sampling or bootstrap resampling? Bootstrap, one easy and effective way to estimate the sampling distribution of a statistic or of model parameters is to draw additional samples with replacement. So from the sample itself and recalculate the statistic or model for each resample. Statistic could be mean, statistic could be proportion. So from the sample itself, and we have to recalculate the statistic or model for each resample. So this procedure is called the bootstrap. Okay. So what is bootstrap? Let's take, this is our original sample, which consists of 1, 2, 3, 3, 4, 7, 6. That's it. Now to create resamples, we have to create a sample replicated huge number of items. See, this consists of huge number of items. Now from here we will be drawing resamples. We will draw lots of samples, lots of resamples. Okay, so after drawing lots of resample, then we will do the enough calculations on top of this. So this is what we call it as a bootstrapping. So in our example specifically, that say salary and years experience, in this example we are using bootstrapping to create a sampling distribution of the regression coefficients for the feature years experience in predicting the target variable. As it is a regression, it's a linear equation, it's a regression. So that is the reason we create a sampling our statistic, our statistic is coefficient. If it is some other cases, we will have a mean as a coefficient. But in this case, mean as the statistic. In some other cases, mean as the statistic. But in this case, we will be taking coefficient as a statistic, because fundamentally coefficient is what influencing the y. Coefficient is what influencing the y through x. So what is coefficient? Coefficient is the amount of the amount it changes, the number of units it changes when 1 unit of x changes, and that's what is your coefficient. So that is the reason here our statistic is coefficient, not mean, not at all mean. Our statistic is coefficient. So that is the reason we will use bootstrapping to create a sampling distribution of the regression coefficients for the feature years experience, because that is our feature and salary is our target. So in predicting the target variable salary, okay, a sampling distribution represents the distribution of a statistic. In this case, again I'm reiterating, it is a regression coefficient. Regression coefficient. So obtained from the repeated sampling from the sample population. So in bootstrapping, we generate multiple bootstrap samples by randomly sampling observations from the original data set with the replacement. So each bootstrap sample is the same size as the original data set but may contain duplicate observations in between the sample or within the sample. Each bootstrap sample is the same as the original data set but may contain duplicate observations. So for each bootstrap sample, we fit a linear regression model using the years experience. For each bootstrap sample, we will fit a linear regression model using the years experience. Okay, after fitting that, then we will go for next step. After fitting linear regression model for each each sample, years experience, feature and salary target variable, we extract the regression coefficients for the years experience, feature and store it in the coefficients list. So after performing a desired number of bootstrap iterations, we have a list of regression coefficients obtained from different bootstrap samples. So this list represents the sampling distribution of the regression coefficients. So by plotting the histogram of the coefficients, we visualize the distribution of these coefficients. The histogram bins represents the range of coefficient values and the height. Each bin indicates the frequency of occurrence. So the sampling distribution helps us understand the variability and uncertainty associated with the regression coefficients. It provides the insights into the range of possible coefficient values and the likelihood of observing certain values. Okay, So I have covered up two steps, 4, 5 in the uh, in one way, at a one go, because I just want to give you overall understanding what happens after taking the bootstrap sample, what you will do. Basically, sampling distribution. What we are trying to do is to create a sampling distribution. So that's why I have put it both. So first thing, the bootstrap sampling is taking a repeated samples from this one at the same, taking a repeated sample of same size, and then calculating the statistic for that, and then creating a distribution. So in this case, ours is regression equation. So that is the reason our relation is based out of the coefficient. As it is a based on coefficient, we are going to create a samples, maybe 1,000 samples, and for each sample we will fit each sample into the regression model. Then each sample will give you a coefficient, and then that coefficients we will plot it as a sampling distribution. I hope till this it's clear. So now what I'm gonna do is I will write a code for this so that it would be much clearer for you. So next step is bootstrapping. So again, most important term here is n iterations. N iterations is nothing but number of samples that you want to take. So I want 1,000 samples. Number of iterations for bootstrapping, or number of resamples that we want to have. Resamples. Okay. So and coefficients. As let's define a empty list for the coefficients so that all coefficients can be appended to this list. So list to iterate through, and list to store regression coefficients, because our relation is based on a regression. So that's the reason the regression coefficient actually influences the target variable. So that's the reason we are taking the coefficient as our regression coefficient as our statistic. Let me call it as a statistic. So here this is test statistic. We call it as a test statistic. Okay. So now it's time to perform bootstrapping. It's time to perform bootstrapping. So let me check for and underscore in your membership operator, and range of how many iterations we have, n iterations, that's 1,000, and then we want to iterate through 1,000 times. So 1,000 times, what it has to do, it has to take a bootstrap sample. So I'm calling it as a bootstrap sample. That's my reference for the object. So df dot, I'm going to use just a sample method from the pandas, and then frac, which is one fraction, and then replace is true. Obviously this is a replace. We are in a bootstrapping, we have to replace the sample, and then you have to take the new sample. So this generate a bootstrap sample, and that we want to do 1,000 times, not once. So 1,000 iteration, this for loop is going to take 1,000 iterations. This for loop is going to be executed 1,000 times. Okay. So then bootstrap sample, in that I want it years experience. That's what is our x, as you know, as we all know. And y bootstrap, again this is also same, but this time we're gonna call up only just y. That's our target variable. Okay. So this time it's just salary. Okay, that's it. So our bootstrap is by and large ready. Let's see how many samples we are gonna generate. Okay, not more than that. Let's execute and see. Okay, there is some issue. Why bootstrap is okay? There is double equal to. Okay, that's it. No issue at all. Now let me see the number of samples that we are gonna generate here. Okay. So for I say I comma underscore in. Okay, let me just copy this y2. I just want to see the number of. This is a separate piece of code. It's not required to include in the main code, so that's the reason I am writing here. Okay, so x and y at this moment it's not required for me, so print just a bit of decoration and another piece of code, print and here sample, let me say I, and let me copy this again, this piece. It's just a bit of decoration, it's not part of main code. I just wanna show you like how exactly things work here. So that's the reason I'm trying to show this, how many samples it's gonna create. That's what I just want to show you. Okay, and let's print it again. This is just to distinguish uh, a sample with another sample. And finally, let's print the bootstrap samples one by one and execute. And here it is. The sample, scroll a little bit down. Yeah, because it's going to take some time. Okay, that's it. Okay, let me, there is, okay, I have to add a small piece of code here in addition to this. So let me, in addition to this iterations, for I just want to add I, and in addition to number of iterations I just want to say a range, let me say enumerate, that's enough, more than enough, enumerate, and let me put start. That's it. This is very nice code to get your data. Yep, that's it. It's going to take some time because it's a 1,000 iterations, but let's see how many samples it has gone through. I'm just okay. Yep, got slow down. Sample one. This is your sample one. You see that years experience and salary. This is your sample two. This is called the bootstrapping. It has been. This is sample two. You see, this is sample three, and this is sample 4. Of course you'll find some duplicates, but that's okay, that happens. And this is your sample 4, sample 5, and you'll find some duplicates. It's part of bootstrapping. You see 17, 17, 16, 16, 24, 25. That's okay, but overall sample 6. And if I scroll down continuously for like this, sample 117, 233, 374, 454, 501, 599, 644, 818, and here it is, the final 1000, the sample 1000. Fantastic. I hope you got the point what I'm trying to say. So these many samples we have generated. This is called bootstrapping. Okay, so now we have to get into the main action. So generating the sample is one step in bootstrapping. Now the main aspect is calculating the statistic, calculating the test statistic for each sample. That's the main important aspect, the next one. So that's what we are going to do. This is also part of bootstrapping, and this is the second step of the bootstrapping. This is very important. That's here our statistic or test statistic is coefficient. So that's the reason, if you just want to calculate the coefficient, you have to apply, you have to regress, you have to apply this regression algorithm to each and every sample, each and every sample. So that's what we are going to do here. So let's say model is equal to linear regression. Obviously this is instantiating the linear regression class object. Then let's call up the fit method from the object, and we have the x bootstrap and y bootstrap here. Obviously you just give it as x comma y, and y bootstrap, this argument for y, and y bootstrap is your target variable, x is your feature. And now I just want to append all these coefficients, because for each iteration you will get a coefficient. So I just want to append each coefficient in each iteration to the coefficients list. So dot append, and so this is, you have to call up the coefficient underscore object and the first term. That's it. So with this, it's been done. If you want to see the coefficient for each, what we can do here is, let me take this one, let me do this, it will be much easier. Yeah, let me print model dot coefficient, and coefficient is equal to and execute, and let's see. I hope it's clear for you. It should be pretty clear. Yeah, it's ready now. So let's completely go up. Let's begin with sample 1, then we'll scroll down to sample 1000, and we'll try to. So the each resample has been fit into the algorithm. So now we have 1000 models because we have 1000 samples. So let's try to get, we have 1000 models out of 1000 samples. Let's try to get the each and every coefficient. Let's see, because the model has been fit into 1000x bootstraps and 1000y bootstraps. You see that it's a reiteration process. It iteratively run through 1000 iterations. So that's the reason we'll have 1000 models, and out of 1000 models you'll have 1000 coefficients. Let's see all coefficients one by one. So let me print model, model dot coef dot and execute, and here it is all. So sample 1, let's see this here. Let's scroll down just a minute. Sample 1 is here. Let me scroll up. Yep, sample 1 is here. The sample 1 93091, sample 2 9694, 9629. These are different coefficients, and if you keep on scrolling you will get the 1000, around 1000. You see that you got around 1000 coefficients, because we have 1000 samples, and to 1000 samples we have fit uh, we have fitted this 1000 samples into linear regression algorithms, and the outcome is 1000 models, and each model consists of a respective uh, each model consists of a respective coefficient. Here what you see. Okay, so with this, bootstrapping step is done, because bootstrapping step is this: you have to draw additional, you have to do the resampling with replacement from the sample itself, and recalculate the statistic test statistic or model for each resample. Okay, till that time we have done. Okay, now it's time to plot the sampling distribution of the regression coefficients, because that's what is the test statistic here for us. So we have to, this is what we call it as a sampling distribution. Remember the name. This is what we call it as a sampling distribution. The distribution which is drawn from the resamples is called as the sampling distribution. So what we are going to do now is, let's plot the sampling distribution here. Okay, let's scroll down. Simple and direct. And here you can see the coefficient matrix consists of all. Let me remove this. At this moment it's not required. If you want, you can actually, let me show coefficients, and here it is your coefficients list. That's okay. Now what I'm gonna do, I'm gonna plot the sampling distribution, the most important step. Plotting the sampling distribution with normal distribution curve. Anyway, that we will add later, but initial focus is sampling distribution for the respective regression coefficients. So plt dot hist, and coefficients, you have to give the list of coefficients as x, and then bins, I'm gonna go for 20 bins. That's more than enough. And obviously it's a density, it's not it's not categorical variable. I'm gonna go for the density, probability density function. Like I have to go for the density, not like categorical. I don't want to put gaps here. Anyway, edge color, that will be explained in later, in later stage. So edge color is equal to, let me go for the black and execute. And okay, let me mention also plt dot show. And this is what you call it as your sampling distribution. So let me give the names, and let me add some plt dot, here it's plt dot x label. X label is a regression coefficients, and plt dot y label, and y label is density, or you can say the frequency on other side. But at this moment, let's say this frequency, density, it should be changed when we use a normal, when we plot a normal distribution curve. At this moment, let's take it as a, okay, let's add it density now only, because anyway we are going to plot a normal distribution curve on top of that. Okay, so, and title sampling distribution of regression coefficients of normal distribution. plt dot legend if it is there, and final one obviously plt dot show, and execute. That's okay, no issue. And this is what your sampling distribution of regression coefficient, and by and large what you got is a normal distribution curve. How fantastic it is, how fantastic. So these are all a regression coefficient. So the most frequent regression coefficient is 9500. It's exactly at the center, whereas 10,500 and 8,500 is very less frequent, whereas 9,000 to 10,000 you got very highest level of probability. The most frequent repeated coefficients are between 9,000 to 10,000, and this is what is called sampling distribution of regression coefficients with the normal distribution. Okay, so now let's move on to the final step, which is inferences, making inferences. So here what will we do? As we have calculated the p-value for the respected uh, initial value, that initially in our example we have done the regression, after that we got the value, na? So for that value we'll calculate the z-score, and then from z-score we'll get the p-value. So now this p-value will be compared with the significance level. If the p-value is lesser than significance level, we'll say that the relation is significant. If p-value is greater than significance level, we'll say the relation is not significant. But what does that mean? What exactly it's happening? How can you tell it's a significant or not non-significant? If it is so, is it a spurious, or it is just is it a mere chance or spuriousness, or is it causality? So these all questions will be answered here. So this is our normal, this is how the this is our sampling distribution. Now let's plot a normal distribution curve on top of this, because it looks by and large normal distribution curve. So I have drawn a normal distribution curve on top of the sampling distribution. So this, if you see, this is our sampling distribution, the histogram, and I tried to fit the normal distribution curve on histogram or sampling distribution. So this standard normal distribution curve that you can see here. Okay, now so these are the regression coefficients that you can see on the screen. But the initial, when we were working on this project, when we are doing the regression on the main sample, of course all these regression coefficients are part of the resamples, but the main sample, the first sample coefficient is 9449.96, and that is here. Okay, that is exactly here. Got it? Now what I'm gonna do is I'm gonna convert this normal distribution curve into standard normal distribution, where this coefficients will be converted into z-score. It's simple. Now we are measuring the distances from mean. We are measuring the deviations from the mean with respect to the values. But when it is converted into the z-score, what is going to happen? We will measure the distance, the same distance, how far one value from the mean in terms of, in units of standard deviation, and that's what has been done now. Now the exact value, the center value mean is 0, and this till here it's a 1 standard deviation, 2 standard deviation, and 3 standard deviation, -1, -2, -3. Okay, basically here more than the standard deviation, it's better to say standard error. 1 standard error, 2 standard error, 3 standard error, because the formula that we have used here is x bar minus mu divided by sigma divided by square root of n. X bar is the mean of the main sample. That's first time we have done a regression, that mean. And mu bar is the mean of the population. That is what is our hypothesis mean, and then divided by standard deviation by square root of n. N is the sample size, standard deviation of the target variable. So we got the standard error. So that's the reason we have standardized this normal distribution. Okay, now as I have standardized the whole normal distribution, whole sampling distribution, so what I'm gonna do is I'm gonna convert this 9449.96, which is a regression coefficient. It is a main regression coefficient, what initially we did. So that we will convert this into z-score. Okay, so that's what we are going to do. But before that, let's do that. Let's convert that into z-score, and let's see what z-score we got. So the z-score that we got for the initial, the main sample regression coefficient is 1.88. If you just want to see, I'll show you just a minute. So this is where we have started. So after the regression of initial, the main sample, of course whatever we are doing is bootstrapping to do the test. Okay, that's one way. But whatever we have done initially, we got the coefficient of 9449 and intercept of this, and sample size is this. This is what is our standard deviation. and this is what the z-score we got, 1.88. Okay, 1.88, because this is what had happened till now in our example. So after that we have calculated the p-value with respect to the that. That is, you keep it aside, that we'll see it later. But this is what the z-score we got, correct, in our main sample. Now with this z-score we want to check in the overall data, in the overall resample, whether it makes a significant relation or not. That's what we are going to check here. Okay, now, so to say you got a z-score of your main observation or main point from the main sample. Now, to say whether it is significant or not, we will be using a significance level. Okay, so now what is significance level? So let's standardize. We have standardized the sampling distribution using z-score. Exactly, that's what we did. Now, so we want to go with a significance level of 5%. So when I go with a significance level of 5% means my probability is 5% or 0.05. So as it is a two-tailed test, as I have told you before also, because my null hypothesis is whether null hypothesis says there is no significant relationship between years experience and salary, whereas alternate hypothesis says there is a relation, whether it is there is a significance relation, whether it increases or decreases, it doesn't matter, but there is a significant relation. So it is a both sets. That's the reason this test is two-tailed test. So that is the reason my 5% will be divided on positive side as well as negative side. So positive side, it will take 1.96. This is the z-score, it's 2. Here it takes 1.96 from this portion till end. This is 1. This is one fraction. Similarly, it will take on left side also, negative side again. That it starts from minus 1.6 till end. Both tails. From 1.96 positive side till tail, and from minus 1.96 from negative side till tail, from left side and right side. And these are the two portions we consider as a rejection area. We consider it as a rejection area because you see your maximum data out of 1,000 samples, out of 1,000 resamples, maximum regression coefficients are falling in exactly center place. You see that here. Here only small portion, just 5%, 2.5% this side. You see that probability is 2.5% this side. Obviously probability is nothing but here it's a frequency. That's it. So 2.5% of regression coefficients are falling after 1.96 z-score, or you can say 10,000 if you want to convert into regression coefficients. And another 2.5% of regression coefficients are falling on left side of minus 1.96 if in z-score value, if you want to tell it in regression coefficients, and in 9,000. So you have 2 point out of 1,000 resamples, 2.5 percentage of regression coefficients are falling below 9,000, and another 2.5 percentage of regression coefficients are falling above 10,000. So that is the reason what we are saying is most of the regression coefficients are falling in between. So very few are falling outside. So that is the reason we consider this as a rejection area. We consider this two outlet these two tails, 1.5%, 2.5 and 2.5% as a rejection area. Now the question is, okay, so with this, for you, what is significance level is clear. The level of significance, we call it as alpha, or we also say it as a type 1 error. I don't want to go into that now because it will be more confused. So level of significance is clear. It's nothing but the probability of rejecting the null hypothesis. That's it. See, our null hypothesis is what? Our null hypothesis says there is no relationship between salary and years experience. When you say, how can you say there is no relation, no relation in mathematical form? The only way to tell in mathematical form is the coefficient should be 0. When y is equals to 0 into x, that actually tells there is no relation. Other than that, some extent of relation is there. So I have taken my sample, I have taken my hypothesized regression coefficient as a 0. If you remember in our previous example, I have taken my hypothesized regression coefficient as 0. So that's the reason. Fundamentally, my null hypothesis says no relation, and that's where it starts here with 0 coefficient here exactly. So if most of the data points which are falling here, okay, supporting the null hypothesis, whichever falling, the regression coefficients which are following outside the 1.96 and outside of minus 1.96 are supporting rejecting the null hypothesis. When you reject the null hypothesis means you are actually saying there is a relation. Okay, so most of the, that's the reason. So 95% of data, for example here in this case, 95% of times it's supporting null hypothesis. Only 5% times it is not supporting the null hypothesis. That's what actually these areas says. Okay, clear now? So now the next important step is comparing. If the p-value is greater than the chosen significance level, in this case it is 0.05. It suggests that the observed relationship could have occurred due to random chance or sampling variability. Okay, let's get into the coding and let's see what's left for us. I think you got the point. So we will just plot it here, whatever is there. Anyway, so normal distribution has been plotted. So what I'm going to do is I will take the z-score. This is what the probability I got. Probability value is 0.05. Okay, that's what my probability value. Okay, so my probability value is 0.05 and our significance level alpha is equal to 0.05. You tell me, just a minute. Yeah, just a minute. Yep, done. So this is p-value. So now let me say whether p-value is greater than alpha or not. That's what I want to see. So p-value is greater than alpha. It's true. P-value is greater than alpha. It's not less than alpha. Our p-value is greater than alpha. So if our p-value is greater than alpha means what? So this is our level of significance. Exactly correct. So here, so what I got, for this z-score I got a p-value of 0.059. It's two-tailed test. Basically it is bigger than 0.05. That means your p-value is falling inside this region, not in the rejection red zone. Okay, so when it is falling inside that, what it is suggesting? It is suggesting that you fail to reject the null hypothesis, because this 95% is from exactly here to here is supporting the null hypothesis. You fail to reject. In this rejection zone only you can reject the null hypothesis. That is the reason when your probability value, if it is lesser than 0.05, then it's going to fall in the rejection zone exactly here. So then we will reject the null hypothesis and we will say there is a significant relationship between the variables. But here in this case our p-value is greater than the null hypothesis. That means it's falling in this region where you cannot reject, or you fail to reject the null hypothesis. That is the reason we fail to reject that there is there is no relationship between two variables. So that's the reason we conclude that there is no statistical significance relationship between two variables. Okay, till now it's clear, it's fine, absolutely fine, no issue at all. But how does it make sense, how does it make sense to say whether there is a relationship or not? Simple, pretty simple. Let's make it very informal to understand this, so that you can understand well. Okay, so here we calculated the p-value by determining the proportion of coefficients in the sampling distribution that are as extreme or more extreme than the coefficient from the original analysis. So in this case, we are interested in coefficients that are extreme or more extreme in the positive or negative direction, depending on the what type of hypothesis we have. So the p-value represents the probability of observing a coefficient as extreme as or more extreme than the one obtained, assuming the null hypothesis is true. So finally, what we did, we compared the p-value to the predetermined significance level, which is 0.05. If the p-value is less than significance level, we reject the null hypothesis. This indicates that the observed coefficient from the original analysis is statistically significant. So, suggesting that the year's experience feature has a significant linear relationship with with the salary variable. On the other hand, this is what had happened in our case. On the other hand, if the p-value is greater than or equal to the significance level, that's what had happened, because our significance, our p-value is 0.059, whereas the p-value is 0.05. So we fail to reject the null hypothesis. This implies that the observed coefficient is not statistically significant, suggesting that there is insufficient evidence to conclude a significant linear relationship between year's experience feature and salary variable. This is where my question begins. When I say there is insufficient for our example, exactly because our probability value is higher than the level of significance, which suggests that there is insufficient evidence to conclude a significant linear relationship between year's experience feature and the salary target variable. So what does exactly mean? What does exactly mean is, let's make it simple. So here you have a lot of regression coefficients from here to here. This is 2.5 percentage probability. Here you have 2.5 percentage of probability. Here you have the most of the probability, 95 percentage. So what we are trying to tell here is, here the regression coefficients exactly at the center from 9,000 to 10,000, the regression coefficients which has a higher probability, they are not merely there because of, they may be because of random chance, or maybe because of variability of the data. So that is the reason it's frequently occurring, because we have done uh, a lot of clubbing the data, a lot of scuffling the data and everything. That's what we did, na? A lot of shuffling we did it in our data. So that is the reason here the regression coefficients which are 9,000 to 10,000, which has a higher probability, you can see the frequency of occurring is very high. So they may occur because of random chance or maybe variability in the data. Whereas if you come to the tails where we have marked red, the probability of occurring is very less, very less, minute. Because from 10,000 to 10,500, if you take a point in that 2.5 percentage probability, as it is going far, going ahead, that's the reason. If your p-value is as less as possible, if your p-value is as less as possible, if it is as less, and you can tell with that more confidence that there is a significant relationship between them. If it is high, you can directly tell there is no significant relationship between them, because the frequency of them occurring because of randomness or random chance or variability is very high, that you can clearly see on the screen. From 9,000 to 10,000, from 9,000 to 10,000, the regression coefficient, the frequency of occurring is very high. That's the reason, the by randomness, by chance, because whatever we have done is a shuffling. We have done the resampling, reshuffling, resampling, reshuffling. That's what we did. So that is the reason. If the probability is high, it means it's because of high randomness. It's because of high variability in the data set. If the probability of that observation, that value, that regression coefficient occurring is less, like 10,000 to 10,500, that means it says the randomness is very less. Maybe that could be a reason of the relationship between them. It's not because of mere randomness. So that's the reason. If our if our p-value is lesser than 0.05, we say that there is a significant relationship between both the target variable and feature, because the randomness, the occurring of randomness, the occurring through randomness or the occurring through variations in the data set is minute. Minute means minute. So that is the reason we say, when we reject the null hypothesis, we say there is a significant relationship between them, because at the end of the day, correlation, at the end of the day, regression coefficient is nothing but the change. The regression coefficient is nothing but the change in 1 unit of x causes this amount of the regression coefficient amount of change in y. So regression coefficient is directly influences the y. So that is the reason the regression coefficient, which has a lesser probability of occurring through randomness or through random chance or through huge amount of variability in data set, there we can say that a relation can be merely because of can be merely strong and significant. That relation can be significant. That relation can be statistical significant. And one more point before I close it, before I wrap it up, I want to tell you is that again, statistical significance doesn't mean causality. Statistical significance doesn't mean causality. Of course, it doesn't mean spuriousness. Spuriousness will reduce, but it's not directly says it is because of causality. Not at all. If you want to understand more about the causality of the data, you have to explore more after getting this. But one thing is, by doing the statistical significance test, you will be more confident. You'll be very confident because you have done the randomness experiment in your data set. Because of that, you have eliminated 95% of regression coefficients which can occur randomly, which can occur through randomness, which can occur to random chance. So that's what is statistical significance test. And this is how you have to understand what is statistical significance test. And when your algorithm does a statistical significance test, and if it gives a p-value, you should know what exactly is happening and what you are doing with that data set and with that p-value and with that significance level or level of significance. And finally, whatever decision you are taking, whether it is saying significantly related or not significantly related, everything you should have some intuitiveness to understand.